Alright, so today we're going to talk about VSEPR theory, and begin our discussion on VSEPR theory, we're going to start with a little bit of history. So, to begin, the discovery of the Lewis structure. The Lewis structure was created by a man named Gilbert N. Lewis, who was a professor at MIT and the dean of chemistry at Berkeley. And Lewis came up with a lot of ideas that helped us in our advancement of VSEPR. The first one is the electron dot theory, which we talked about last time with our electron Lewis structures. The second part was the octet rule. So a molecule always wants to have an electron configuration that is similar to that of a noble gas, so with 8 electrons surrounding it. And finally, the repulsion theory, that these electrons surrounding a molecule always want to have the largest amount of space between them. Following in Lewis's footsteps, 2 more male scientists decided to work with VSEPR theory. Their names were Sidgwick and Powell, and together they created VSEPR theory as we know it today. Because of their contributions, we have been able to build on VSEPR theory and expand it. To further the development of VSEPR theory, 2 men in the 1950s and 60s worked very hard with inorganic chemistry. The first man, Ronald Nyholm, worked predominantly with the transitional metal compounds. The second man, Ronald Gillespie, studied the importance in the geometry. Together, they developed VSEPR theory, and they emphasized classical bonding pictures, included quantum theory, but they predominantly focused on electron clouds of varying density. Before we dig in how to do VSEPR theory, I think it's necessary to review how to write Lewis structures. So we know that Lewis structures happen because atoms bond to decrease the potential energy and because it results in a more stable configuration. And these atoms bond together by either transferring electrons or sharing them. So last time we talked about our steps to draw Lewis structures. Step 1, you need to write the correct skeletal structure for the molecule. After that, we're going to calculate the total number of electrons by adding the valence electrons together. And we know we can find these numbers from the periodic table. After we figure out how many electrons we need, we should distribute the electrons by making duets, which is when we draw the dots surrounding the molecule. And finally, if any of our molecules lack an octet, we're going to rework them and try and form double or triple bonds. Okay, so finally, let's talk about what VSEPR theory really is. VSEPR is an acronym that stands for Valence Shell Electron Pair Repulsion. And VSEPR is a theory, and it's the idea that electron groups repulse each other, and this repulsion determines the molecular geometry. An electron group is any type of lone pair, single bond, multiple bond, or single electrons. Electrons repel one another to create a state in which all of the valence electrons are the maximum possible distance from one another. And for a molecule with one central atom, the geometry is based on the amount of electrons bonded to the atom and the amount of lone pairs on the atom. Alright, so in VSEPR theory, we have 2 different types of geometries. The first geometry that we're going to talk about is electron geometry. So electron geometry includes the arrangement of all electron groups. And there are 5 main types of geometry a molecule can assume when it is doing electron geometry. These are linear, trigonoplanar, tetrahedral, trigonal bipyramidal, and octahedral. And in a moment, I'll go deeper into these 5 main topics. The first electron group that you can have in electron geometry is a 2-electron group. And a 2-electron group forms a linear geometry. There are 2 atoms bonded to the central atom, and as we know, that electrons would like to have the furthest distance from each other, so the bond angle will be 180 degrees. The next electron geometry is 3-electron groups geometry, which has a trigonoplanar geometry. And so in this geometry, we have 3 atoms bonded to a central atom, and the bond angle is 120 degrees. Next, we have 4 electron groups, and this creates a tetrahedral geometry. And in a tetrahedral geometry, we have 4 atoms bonded to a central atom, and the bond angle is 109.5 degrees. Next, we have 5 electron groups, and this will form a trigonal bipyramidal geometry. In this geometry, 5 atoms are bonded to a central atom, and the bond angles will be 120 degrees along the electrons on the equator and 180 degrees on the other 2. The final electron geometry is the 6-electron group, which will form an octahedral geometry. In an octahedral geometry, 6 atoms will bond around one central atom, and they all will form a 90-degree bond angle. Before we transition into our next VSEPR theory geometry, I think it's important to understand what exactly a lone pair is, because lone pairs will be the distinguishing factor between our two geometries. So lone pairs are non-bonding pairs of electrons, so this just means they aren't shared with another atom. Lone pairs, characteristically, are highly repulsive. They decrease bond angles because lone pairs repel more, and they're closer to the nucleus. The second VSEPR theory geometry that we're going to cover is molecular geometry. And molecular geometry is another geometrical arrangement of the atoms, but this time we're going to need to distinguish between the lone pairs, which are unbonding, and the bonding pairs. So when we do this, if a molecule does not have any lone pairs, its molecular geometry will be similar to the electron geometry. And if a molecule does have lone pairs, it will have a molecular geometry that differs from the electron geometry. To determine the molecular geometry of a molecule, we're again going to write out the steps. The first step to determine the geometry is to draw the Lewis structure. Once we draw the Lewis structure, we're going to cover up the lone pairs and determine the geometry based only off of the bonded atoms. Once we determine the geometry based off the bottom atoms, we're going to refer to table 10.1 from the textbook to label it correctly. And 10.1 is going to be an extremely important table that you will need to memorize for your exam. Alright, so here's a picture of table 10.1, the electron and molecular geometries, and this is on page 434 of the textbook. And you guys, you really need to memorize this table for the exam.
Okay, so to work an example problem of a VSEPR theory without any lone pairs, we're going to use the molecule CHCl3. The first step in working any VSEPR problem is to draw out the correct Lewis structure. Then you're going to identify your central atom. Your central atom is the one that most of the bonding groups are connected to. So in this example, our central atom is carbon. Then you'll want to identify the number of electron groups. Here we have 1, 2, 3, 4 electron groups. Now you'll see that there are no lone pairs in this example, as all of the electrons have mates. And we know hydrogen only has one electron to give, so therefore it is full also. So we've identified that there are no lone pairs. Now we need to figure out how many bonding groups there are. Well, if there are 4 electron groups and no lone pairs, then there must be 4 bonding pairs. From this information, we can then identify the electron geometry and the molecular geometry. We'll do this by looking at our table 10.1 from the textbook. This table shows examples of each of the electron group numbers with bonding groups or lone pairs. So if we look up 4 bonding and 0 lone pairs, we look over here and we say 4 bonding and 0 lone pairs. So the electron geometry has to be tetrahedral. If we look at the molecular geometry, it is also the same. Molecular geometry is focused on the amount of lone pairs you have. Since we have none, then the molecular geometry will be the same as the electron geometry.
Electron geometry and the molecular geometry of carbon disulfide.
To start working out this clicker problem, we're going to write the molecular structure of carbon disulfide, which is CS2. The Lewis structure will then tell us that the carbon is double bonded to the sulfur atoms. The sulfur atoms being double bonded, this bond is treated just like a single bond would be. So if we place the electrons around the Lewis structure, we can then determine the bonding groups, or the lone pairs. So the total number is 1, 2 groups. We see that there are no lone pairs on this example. Taking this information, we'll be able to find the electron geometry and the molecular geometry. If you reference 10.1, this is a good study guide. You'd probably need to memorize this to be able to work these problems efficiently. If we look up 2 bonding groups and 0 lone pairs, we'll see the electron geometry is linear. Also, since there are no lone pairs, the molecular geometry is also linear. As a follow-up to this clicker question, what does a linear molecular geometry say about the bond angles in carbon disulfide? If you look, you have a linear molecular geometry. Linear means a straight line. So the molecule is basically attached and lays flat. This means that the bond angles are right here. This is 180 degrees for their bond angle. To work through this example problem of a VSEPR problem with lone pairs, we are going to use the example CLF3. The first step in tackling any VSEPR problem is to work out the Lewis dot structure. The Lewis dot structure will allow us to be able to determine the number of bonding and lone pair groups. The next step is to determine the total number of electron groups off of the central atom. Now in this problem, our central atom is Cl, or chlorine. The total number of electron groups that are attached to this is 1, 2, 3, 4, 5. Now from these electron groups, we can determine if they are lone pairs or bonding groups. Lone pairs, again, are ones without a mate. As we can see in this example, all of the following have pairs, so there are no lone pairs. There are, however, 5 groups, so there must be 5 bonding pairs. The next step is to determine the electron geometry and the molecular geometry. If you look at table 10.1, we know that for 5 electron groups, 5 bonding, and 0 lone pairs, then the electron geometry is trigonal bipyramidal. The molecular geometry will be the same. This is because there are no lone pairs. Now, if we want to look at the bond angle, this is where this problem gets unique. Since there are 5 pairs and the trigonal bipyramidal makes a shape like this. Here is the central atom. The surrounding atoms are not all shown on the same plane, meaning the angles of where those are attached are not going to be the same. So around the equator of the central atom, the bond angle is going to be 120 degrees. However, for those that are not on the same plane, the bond angles are going to be slightly different. These are the equatorial ones, and right here you can see the 90-degree bond angles. So, for the axial bonds, the bond angle will be 90 degrees.
Next, I want you guys to identify the electron geometry and the molecular geometry of the molecule of iodine difluoride with a -1 charge.
To work out this clicker problem, the first step, as always, is to draw the Lewis dot structure, with iodine being the central atom and the fluorine attached on the sides. We can draw this Lewis model. However, we see that this molecule has a -1 charge. So when drawing the Lewis dot structure, you'll put the entire molecule in brackets and signify a negative charge in the top right-hand corner. If we look, we have to see the bonding electron groups and the lone pair electron groups. So for the bonding, we're going to have to look up the total number. The total number is 1, 2, 3, 4, 5. So if there are 5 groups total, if we start looking, at first it would seem that all 5 were bonding, but you have to take into account this negative charge. This shows that we are going to have some lone pairs. For this molecule, it is unique in the fact that the bonding groups are not all arranged as you might think that they would be. The lone pairs come from the iodine-connected bonding groups. So there are 3 lone pairs and 2 bonding pairs, because both of these add up to 5. The electron geometry and the molecular geometry can then be found. If you notice, this appears to be lineal, meaning it's in a straight line. However, when we go to our chart and realize that for 5 electron groups, 2 bonding pairs, and 3 lone pairs, the electron geometry is not linear. It's not lineal, it's not in a straight line. The electron geometry is trigonal, bipyramidal. However, you'll notice that the molecular geometry is indeed linear, showing that the lone pairs, how many lone pairs there are, do affect and change the molecular geometry. If we look at this, even though these are different, the molecule is linear, so it lays in the same plane. So the bond angles would indeed be 180 degrees. Here we have a more difficult problem. With the molecule CH3OCH3, we notice there's going to be maybe more than one central atoms. I've set up this chart to help walk you through this problem, but as always, the first step is to draw the Lewis structure. So if we start with the center, we'll see that there are indeed 3 central atoms, and off of these atoms are the bonding groups. So after we've drawn the Lewis dot structure, we can start to maybe try to fill in our table that we have set up here. So off the first carbon, we're going to call this carbon 1, and we'll call this carbon 2. Off carbon 1, we see we have 1, 2, 3, 4 electron groups. If we look for the number of lone pairs, we see that there are no lone pairs in the carbon 1 bonding groups. So if we know there's no lone pairs, we know there must be 4 bonding pairs. So if we look up the molecular geometry for 4 electron groups, 4 bonding groups, and 0 lone pairs, we'll see that the molecular geometry is tetrahedral. Now, if we want to look up at the center oxygen, we're going to start counting its bonding groups. And we have 1, 2, 3, 4 bonding groups. Well, if we have 4 bonding groups, and we look for the lone pairs, we see that there are 2 lone pair sets. If we have 4 groups, 2 lone pairs, then we must have 2 bonding pairs. If we look over at table 10.1, that shows that there's a bent molecular geometry. Bent resembles sort of a triangle shape. 1 atom's on the top and 2 are sloping down at the sides. This is a common molecular structure. Water has this structure. Alright, now we want to look at the carbon 2 molecule. So let's count its electron groups. 1, 2, 3, 4. And again, there are no lone pairs, meaning there are 4 bonding pairs. Carbon 2 looks identical to carbon 1, so its molecular geometry is tetrahedral. Now, where problems like this kind of get a little sticky is if you're asked to sketch the molecule. So if we're going to sketch the molecule, let's start with the oxygen molecular geometry because we know what it looks like. So if we draw our oxygen, and we're going to kind of bend the lines down to the carbons, just like the bent molecular geometry. Now we have to worry about the hydrogen bonding. So if they're tetrahedral, a tetrahedral shape looks kind of like this. You have your central atom, and those bonded around are sort of at angles. They're going to spread themselves out as much as possible because they want the energy to be spread out as much as possible. But as you can see, this one should be sticking out the back like it's sitting on a tripod. However, if you draw it like this, it kind of looks like this bond angle is shorter than this one, which is not the case. So to do this, we need to spread these out as much as possible. Since there's 3 on each, we're going to pull 1 hydrogen back on each carbon. And that's going to stay in the same plane as the carbon. So that's why it's just simply bonded like this. However, to help us realize the dimensions and see that this isn't flat, it isn't 2D, we have some symbols that help us show different dimensions. And all these are is to show that these are not on the same plane as the carbon. So if we connect the other 2 hydrogens like so, we'll do the same thing down here. This way, we are able to see a correct and more accurate sketch of the molecule. And this will show that this isn't a 2D structure. It is 3D and it pops out on different planes.
Alright guys, now it's your turn to try. Determine the molecular geometry for iodine tetrabromide.
I'm just going to walk you through this clicker question, and it's best when they're difficult like this to walk it through in steps so you know from beginning to end what you're doing, and you can determine where you messed up if need be. So step 1 is always to draw the Lewis structure. So for here, iodine is our central atom, and we're just going to attach the Br molecules around it like this. If we assign the electrons to show the valence theory, the valence electrons, then we have a Lewis structure. However, the molecule we were asked to find the molecular geometry for has a negative charge. So we're going to put the entire structure in brackets and dictate a negative charge in the upper right-hand corner. So for step 2, we're going to determine the total number of electron groups. To do this, we're going to see that it's off a central atom, which is the iodine. So we have 1, 2, 3, 4, 5, 6 electron groups. Now, out of those 6 electron groups, we have to determine which ones are bonding groups and which ones are lone pair groups. So for this, we can see that we have 2 lone pair groups and 4 bonding groups. Now, for step 4, we're going to use the information that we determined in step 3 with the bonding groups and the lone pairs to find the molecular geometry and the electron geometry. So if you look at table 10.1, for 6 groups, 4 bonding, 2 lone pairs, we're going to see the electron geometry is octahedral. And the molecular geometry is square planar. Now, what makes these problems difficult is you're not done. Now we're asked to sketch the molecule. If we're sketching the molecule, then we're going to have to know something about the bond angles for a molecular geometry of square planar and an electron geometry of octahedral. Now, today we have table 10.1 with us that tells us that for square planar we have 90-degree angles. However, table 10.1 should be memorized as you're not going to have it on your exam, and it is vital to working any VSEPR theory problem. So, if we see that our bond angle is 90 degrees, what does that mean? Well, for square planar, the molecule kind of looks like this. You have your central atom, and the bonding atoms are all arranged off of the central atom, kind of catty-cornered off the atom, all at 90-degree angles. This is really nice because it shows that it is easily represented on a 2D or on a piece of paper for us to see the model. So for step 6 and our final step, we're going to sketch our molecule. Now, we know that our central atom is iodine, so iodine is going to go in the middle. And we're going to attach the remaining atoms off the sides of the central atom, and you can see that there are 90-degree angles here. However, it's here where you need to reference back to this negative charge. So again, you're going to take the entire molecule, place it in brackets, and notate a negative charge in the top right-hand corner.
Although VSEPR theory works the majority of the time, there are still some exceptions. One of these exceptions is when it comes to transition metals. Many of these transition metal compounds don't work according to VSEPR because they have unusual geometries. And this unusual geometry is due to the absence of lone pairs in the valence shell and also to bonding interactions of the ligands within the D subshell. Alright, so here are a few memory aids to help you memorize the VSEPR theory. Linear means a straight line, therefore it resembles one. For trigonal planar, the prefix tri means 3, so it will have 3 electron groups. Tetrahedral can also be broken down. The prefix tetra means 4, so again it will have 4 electron groups. Trigonal bipyramidal, again tri equals 3 and bi equals 2 for a combined 5, so we will have 5 electron groups. Octahedral, however, ruins this small trend, but just remember it will have the most electron groups of all. In VSEPR theory, there are no basic trends because molecular geometries are repeated with varying electron geometries matched to it. So for example, let's say we have 2 molecules and they both have a molecular geometry that is bent. But what's the difference between the two? Well, the first one, it has an electron geometry that is trigonal planar, and this is because it has 2 bonding groups and 1 lone pair. The other one, which has a molecular geometry of bent, has an electron geometry of tetrahedral, and this is because it has 2 bonding groups and 2 lone pairs. Even though they have different electron geometries, they will resemble each other and they both will have a bent-shaped structure. Before we conclude our discussion of VSEPR theory, it is necessary to understand real-world applications. One example is artificial sweeteners. Artificial sweeteners taste sweet because they fit into the receptor pocket that sucrose normally binds to. VSEPR theory has allowed us to create a geometry similar to the sucroses. The knowledge of VSEPR molecule geometry allows us to create products such as this. Thank you for listening to our presentation over VSEPR theory, and I hope that you learned something.